big omega and theta. This denotes the upper bound, and this denotes the lower bound, and this is the exact complexity. And in the respective definition, the inequality is here less than or equal to, here greater or equal to, here both less than and less than or equal to and greater or equal to, right? So that means we can say theta equal to big O intersection omega. Anyway, this is a set, this is a set. Yesterday we have seen that, right? This is actually a set. So big O intersection big omega actually gives the theta. Okay. So this is also another important point you have to note down. And we will describe in the algorithm the various complexities, various types of complexities are possible, and there are some specific names for those things. And just for you to know that, let me explain that. Suppose we have the complexity something like order of 1. So order of 1 actually that is a constant, right? Any constant can be stated as order of 1. So this is called a constant value, right? The constant. So whenever the complexity is order of 1, we say that time complexity is constant. And if we have the complexity like order of log n, then that will be named as logarithmic complexity. Logarithmic complexity. And sometimes we may have something like order of log n power c, like that. So this can also be stated like order of log n into the power c. Okay, sometimes we may use this notation. Mostly we use this notation. And if the complexity is like that, then that is called polylogarithmic. Okay, polylogarithmic. And if the complexity is like order of n, then that is called the linear. And if the complexity is order of n log n, then that will be stated as linear arithmetic. Okay, linear arithmetic. And if the complexity is order of log n square, that is called quadratic complexity. And if it is order of n cube, that is cubic complexity. And if it is order of okay, next page I can take. If it is order of n power c is a constant. Okay, so wherever we use c, the c is a constant. N is the size of the input. So if the complexity is order of n power c, that is called polynomial complexity. Polynomial complexity. And if it is some constant power the size of the input, c power n, then the complexity is said to be the exponential. And if the complexity is like n factorial, that is a factorial complexity. So like that, some terminologies are there. So maybe when you refer at a research paper or textbook, they might have used somebody they say that algorithm is of polynomial complexity. So you should know that what the polynomial complexity means. Okay. So for that only, I have given various terminologies used in the algorithmic complexity. Okay, now we are going for an extension to the asymptotic notation that is called conditional asymptotic notation. Conditional asymptotic notation. So sometimes whenever we are describing the complexity, we have to state based on certain conditions. So if the complexity is derived with respect to certain conditions, then it will be a conditional asymptotic notation. So one example I can say, I think you might have studied about merge sort. Have you studied or not? Merge sort algorithm?
No, sir, we haven't.
You haven't studied. Okay, I think sometimes for C language until they used to give. Okay, no problem. So I can explain the thing. Merge sort. There the problem is we have to sort n numbers. Okay, we assume that there are n numbers available. Okay, And what we do is we split the problem into almost equal half. Why you say almost equal half? The thing is sometimes the number of elements is odd. So one half will be having one number less compared to the other one, right? So we split into almost half. Then what we do is we apply merge sort on this, and we apply merge sort on the right portion. So that means, I mean, once again, when you call the algorithm, this will also be split into two, then that will be repeated. So finally, what happens? You will be having only one element. So if the problem instant is having only one element, that is already in the sorted. Then what we do is, I mean, now conquer phase. Okay, conquer phase. So the result of two things will be combined to get a larger sorted sequence. For example, we assume that we are applying merge sort. Actually, the problem is applying merge sort on the whole problem, and the size of the problem is n. Okay, that means there are n elements are available. Okay, how we are doing that is that problem is split into almost two equal halves, and we recursively apply. And the recursive algorithm, you know that, right? Recursive algorithm. So we can call the algorithm within itself. Okay. So we can apply merge sort on this. We can apply merge sort on that. And if you completed the recursive call, what happens? You get a sorted sequence. Now from these two sorted sequences, we have to get a single sorted sequence. That is combination of these two. How we can do that? So we can take this element and this element. We can compare. Okay, anyway, this is in increasing order, this is in increasing order, because these two are already a sorted sequence, right? So what we can do is, you can take the first element, that is the least element in both the things. You can compare these two elements, whichever is smaller, that can be written into a new array. Okay, maybe you can say that this is lesser, okay, without loss of general. If this is less, then that will be coming here. So we can assume this is lesser, then that element will be moved here. Then we will advance this to next element. Then this element and this element will be compared, and whichever the least, that will be taken. Once again, if this is least, that will come. Then if this is the least, then next element will be taken. These two will be compared, and if this is least, then that will be coming here. Then in this case, next element this, and then this and this will be compared. So if you do like that, finally we get a single sorted sequence. So this is what the merging phase or conquer. Okay. That's why this is called the merge sort algorithm. That's why this is called the merge sort algorithm. So same thing actually we are repeating for this subproblem also. So same thing, we divide it into two things, do it, then again dividing into two things. Then the conquer phase, if you do like that, finally you get a single sorted sequence. So this is the overall description of the algorithm. Anyway, we cannot go much detail in that. Anyway, we are looking at only the complexity part. Maybe later on, whenever we are discussing this, anyway, I think this is not in your syllabus. Okay, so in the divide and conquer strategy. So if it's required, then we can see the detailed algorithm. Okay, now only the description algorithm, that would be sufficient. So this is what we are doing. Now, whenever we are trying to write the complexity, anyway, already we have seen a problem that is called finding the largest element present in the array, right? So therein we have seen how to determine the time complexity as well as space complexity. So here we are trying to say only the time complexity. Anyway, just our idea is how to represent the conditional asymptotic notation. Okay. So if you are calculating the time complexity, anyway, the time complexity is a function, right? Function in terms of the size of the input. Let me say that f of n is the time complexity, the function related to the time complexity of doing the merge sort of n elements. Okay, suppose we assume that f of n is the function, because anyway it's a function only. Maybe you can get 4n plus 15 or 4n plus 3, something like that. So this is a function, right? So the function, I am saying that f of n. So I assume that anyway I do not know what the complexity here except how much, because I haven't written the algorithm or anything, but I know the logic. Okay. So based on this logic only, I'm going to write the algorithm. So if I write the algorithm, there are two recursive calls. So based on that, we can write what the function is. So if we assume that f of n is the time complexity of doing merge sort for the size of the input n, then this can be stated as, anyway, this problem, how we are doing is, given an array of size n, that array will be divided into almost two equal halves. Okay, so you can assume that two equal halves. Okay, in that case, there are two such problems we are getting. Okay, there are two such problems getting. But those two problems again we are applying the merge sort. But what happens is the size of the input is reduced by half, right? Because total elements I am dividing it into two. Then there we are applying the merge sort algorithm. So the size of the input is half. Therefore, there are two such problems. Each problem of size n by 2. So whatever the complexity required for merge sort algorithm, but the size of the input is n by 2. For that value, we will get that, right? So now if you spend this much time, then you get a sorted sequence here and another sorted sequence here. Then to get the overall sorted sequence, all what you have to do is you have to do the merging. But how we are doing the merging? We are taking one element from this array and another element from this array. Those two elements are being compared. Whichever is minimum, that will be moved to the new array, something like that. But each comparison, when we are comparing two elements, one element will be moved to the output array. Okay, then after that we are going for the next comparison. So each comparison, one element is being moved to the output array. So how many such comparisons are required? Okay, the number of comparisons that is required is n minus 1 comparisons that is required. Okay, n minus 1 comparisons that is required. But the last element, anyway, that's only one element that can be moved. Therefore, the time spent for doing the merging is n unit of time. Okay, comparing and moving. So n elements to be moved here. Compare and move it. So the extra time that we have, this is for doing the merging. This is for doing the merge sort of the sub arrays. So now what we get is we get a function. Okay, so this function is called the recurrence function. So whenever the algorithm is a recursive algorithm, we can always write the complexity in form of a recurrence relation. Recurrence relation means the function is being used within it, right? So this is a recurrence relation. Okay, now this is not the way we represent the complexity. So the complexity represents something using the asymptotic notation, big O or big omega, theta, something like that, right? So anyway, we are interested in knowing the upper bound. Therefore, we are trying to put it in a big O notation. So how we get the big notation for this complexity? So anyway, based on the algorithm design, what we have done, based on the logic, we have derived the function. That function is a recurrence function. Now, if you solve the recurrence function, then only you get the complexity, a time complexity, okay, in terms of the big O notation. Okay. Therefore, let us see how we do that. If you want to do that, we have to make some assumption, so that will be better. So there are several other methods are available. Anyway, those parts are not there. In your syllabus, but one easy method, maybe I can tell you. After one or two classes. Okay, so for the time being, only the easiest way of knowing it, I can tell you. So f of n is equal to 2 times f n by 2 plus n. Okay, now if you want to solve that, I am making the assumption let n is equal to some 2 power k where k is a constant. So n is equal to 2 power k where k is a constant. So that means number of elements in the array, that is only the assumption. It is not exactly. So sometimes 10 elements are there. 10 is not a power of 2. Okay, but at the same time, if 16 elements are there, it's a power of 2. So anyway, we are making the assumption that if there are 2 power some constant, that is 2 power k elements are there, then it is easy to solve this recurrence equation. So if I make this assumption, what I am doing, because the denominator is having 2, so that's why I have taken like that, right? Denominator is having the value 2. So if I take n is equal to power k, then this division is always possible. So that's why I have taken like that. So if you substitute this value, then what happens? This is f of 2 power k, right? So n is equal to 2 power k. Therefore, this is f of 2 power k. So that is equal to 2 power f of 2 power k minus 1, because 2 is at the denominator, so we can cancel it, right? So if you cancel it, remaining is f of 2 power k minus 1, then plus this is n 2 power k. Now you see the fractional part that has gone. When you take this assumption, the fractional part that goes up. So we have to remove that, and if you remove that, then automatically that will be in a simplified representation, so that we can solve it quickly. So that's why we are making the assumption. Okay. Now you see once again the same value can be applied here. The recurrence function, these are recurrence function. This function can be applied here. So if I substitute the value here for this f of 2 power k minus 1, what do you get? 2 f of 2 power k minus 2, right? Plus 2 power k minus 1. So if I apply the function again for this, we get this, okay, and another 2 power k is there in the outside. Okay, now what happens? This is equal to 2 power 2, 2 into 4, and I am not writing 4 straight away because I have to get a pattern. Therefore, I am writing 2 power 2 instead of writing it as 4. So 2 into 2, 2 power 2, and this is f of 2 power k minus 2, and this 2 into this is equal to 2 power k, right? This 2, if you multiply this 2 with this is 2 power k, and another 2 power k is also available here, right? So 2 power k. So now what happens? So that is equal to 2 power 2 f of 2 power k minus 2, plus there are 2 times 2 power k is there. So I can put 2 times 2 power k is there. Okay, once again for pattern I am not multiplying this. Okay, just I am writing 2 times 2 power k. So once you apply this function one time, one iteration, you are getting this one. So similarly, if you apply next time, again if you apply that, what you can see is you can get something like that. So 2 power 3, so 3, so one more time, and once you apply it will be 2 power 3, f of 2 power k minus 3 plus 3 times 2 power k. So this is what you get. Anyway, you can apply and check later. Okay, I think it's not this one. Okay, you can apply and see that, right? So if I proceed like that, so k times if I do that, we proceed like that, and k times if I do that, we get 2 power k, f of 2 power k minus k is 0. So 2 power 0 is 1. So that is f of 1. Actually, anyway, here you see this recurrence relation. If you take f of 1 what it means? So the complexity of the multi-sort algorithm, if there is only one element is there, only one element means we are not spending any time for that. We can straight away write the value as an output, right? So that means f of 1 is always 1. F of 1 is equal to 1. So this is the initial condition. So whenever we have a recurrence relation, there will be an initial condition. Okay. So to find the particular solution. So we can assume that the f of 1 is equal to 1. Here what we get is, if k times we repeat, this will be 2 power k, and this is f of 2 power k minus k. K minus k means 0. So 2 power 0, that is f of 1, plus this is k times 2 power k. K times 2 power k. Anyway, this value I can write here. Okay. Anyway, I cannot move the note a little above. So if this value, if you take that 2 power k, okay, f of 1 is equal to 1. So I am not writing that based on this, and this is k into 2 power k. So now what happens? The inner function that has gone, right? So f of 2 power k is equal to, actually this is equal to f of 2 power k. F of 2 power k is equal to this value, we get that. But you see, this is not our answer. Why this is not our answer? Because we know that whenever we are representing the time complexity, it must be stated in terms of the size of the input. So as far as this problem is concerned, the size of the input is n, not k. So actually here it's 2 power k. K is a variable here, right? So it is not in terms of k, but it is in terms of n. The size of the input is n. So what we have to do, we have to convert it back to n. So then only we get the final answer. How we can convert that? Anyway, we know that n is equal to 2 power k. So this is equal to n, right? So n is equal to 2 power k. So here also this 2 power k is n, and k value we have to know that. Okay, this 2 power k equal to n and k. So that means if n is equal to 2 power k, then if you take logarithm on both sides, you get log n is equal to k. Okay, that is here logarithm to the base 2 actually. So normally in algorithmic complexity, we take logarithm. If you say log of n, it is log of n to the base 2 unless otherwise it is stated. Okay, if for some other base, then we will state that. So you can assume that if the base is not given, it is base 2. So we are taking log to the both sides, then k is equal to log n to the base 2. So then what you get? You get this 2 power k is equal to n, and k is equal to log n. So n plus n log n. So now you see the values in size of the input. Now already we have seen the property that order of f, okay, plus order of g means order of maximum of these two. So this is our f, this is our g. And also we know that f is order of itself, right? The function is order of itself. So this can be stated as order of n. This can be stated as order of n log n. And based on the first property, we have to take the maximum. So out of these two quantities, the maximum is order of, okay, so maximum is n log n. So we can say that order of n log n. But when? That's the question. When this will be order of n log n? So how we get this n log n? Based on this assumption. Okay, based on this assumption. If this assumption is not hold over, then we cannot conclude because we have assumed something. Based on that, we solve that. Therefore, what we say is order of n log n when n is the power of 2. Okay, that is a condition we have taken, right? N is the power of 2. So here one condition we have given, therefore this is called conditional asymptotic notation. So this condition can be removed. Anyway, that also I can tell you that when this condition can be removed. So anyway, this is the conditional representation. I can come to that part later on. Now we have to see the definition of conditional asymptotic representation. So now you understood that why we are going for the conditional asymptotic notation, right? Okay. Here, once again, we can take then two functions f and g from set of natural numbers to set of non-negative real numbers. And if you say that f of n is equal to order of g of n when a of n. So a of n is a condition. Once again, you remember this a of n is also function in terms of n because we say that here n is a power of 2. N is a power of 2. So therefore, there is also a function in terms of n, right? So therefore, we are saying that f of n is equal to order of n, order of g of n when a of n. So this is our condition. This is the complexity based on this condition. So how we define that is, if we say something like that, then we say that there is a constant c belongs to R, and there is a constant n belongs to n. This is similar to the previous one, right? Such that this a of n implies. Now we have to say that this condition implies. So only when this condition implies. So therefore we say a of n implies. Okay, this f of n is less than or equal to constant multiple of g of n. So this is what we are saying. Only when this so this condition implies this, and this for all n greater or equal to n. So this is the definition of conditional asymptotic. Sorry, this is the definition of conditional asymptotic representation. So you see these parts are similar only. Only here there is a difference. Only this condition implies that. Otherwise it won't be. Okay. Now the question is, anyway, already we have taken the merge sort algorithm and we have seen the function as f of n is equal to 2 times f of n by 2 plus n. And how we solve that is, we assume that n is a power of 2. N is a power of 2. But the question is, whenever we are running the algorithm, multi-sort algorithm, number of input need not be a power of 2. Anyway, we never say that always we give only 8 elements, 16 elements, or 32 elements. So these are all power of 2. So we cannot say that. Sometimes we may give 25 elements, or sometimes we give 100 elements. But these values are not power of 2. Therefore, now the question is, anyway, I want the complexity not for a particular cases, but I want the complexity for all the instance sizes or input sizes. Okay. Therefore, what we want is we have to remove the condition. How do you remove the condition? Remove the condition. There are few more things we have to see that when the condition that can be removed. For that, first let us see two definitions. Okay. Let us see two definitions. The first definition is eventually. Okay, eventually non-decreasing function. Non-decreasing function. So that means if there is a function f from set of natural numbers to set of non-negative real numbers, Okay, non-negative real numbers. And if you say that this f is eventually non-decreasing, then what we say is this f of n is less than or equal to f of n plus 1. Once again, for all n greater or equal to n naught. Okay, eventually means there exists n naught belongs to n, such that this inequality holds good for all n. Once again, you see this is asymptotic only. For large value, maybe for lesser value it may or may not, does not matter. But after a certain point, if the condition satisfies, that's fine. So here you see equal to condition. That's why we are saying that non-decreasing. So if you, that's why we are not saying that increasing function. Increasing means equal to cannot come. Okay, only strictly less than will come. So it's eventually non-decreasing. Therefore, less than or equal to, we are saying that. So when n increases, automatically the function value will also increases. So that's what we want to say that. So eventually non-decreasing, because this one is for all n greater or equal to n naught. Maybe for some values less than n naught, it may not no problem. But when n becomes larger, this condition to be satisfied. This is one definition that we need. And one more definition is called p-smooth. P-smooth. So here let us assume the let p greater than or equal to 2 be an integer. Let p greater than be an integer, and let us assume that f from set of natural numbers to set of non-negative real numbers is an eventually non-decreasing function. Okay, already we have seen what is eventually non-decreasing function. And if we say this function is p-smooth, we say this function is p-smooth, then it should satisfy f of pn, that is p into n. F of pn, that is equal to order of f of n. So if you take f of pn, then that will be equal to the order of f of n. Then we can say that the function is p-smooth. Function is p-smooth. So these two definitions we need that. Based on these two definitions, there is a theorem, but anyway, we are not going to see the proof of a theorem, only statement is sufficient. Only the statement is sufficient. So what the theorem that says is, let us assume that p greater than or equal to 2 be an integer. Okay. Then two functions, that is f and g, both from set of natural numbers to the non-negative real numbers. Okay. Both the functions we take that. These both the functions are eventually non-decreasing, and G is p-smooth. So if these things are satisfied, then if you have the complexity like that, so if f of n belongs to, okay, now I am saying belongs to, right? Belongs to order of g of n when n is a power of p, n is a power of p, so this implies, okay, we can say f of n is equal to order of g of n. Okay, the theorem statement is very important, and proof is a little lengthy, and that is not required for you. Okay, so here you see that the f and g are eventually non-decreasing function, and the g is p-smooth. If these conditions are been satisfied, then what you can say, you can, if such condition is there, that condition can be removed. Okay, if n is the power of p means p-smooth. If n is the power of 2 means 2 smooth. N is the power of 3 means 3 smooth. So that's why we say p greater than or equal to 2 be an integer, something like that. Okay, now let us take our merge sort algorithm. Okay, so merge sort algorithm, already we have got the conditional asymptotic value. Now that condition that is to be removed. Okay, based on this theorem. So what is the function? The complexity of the merge sort algorithm, that is f of n is equal to 2 times f of n by 2 plus n. So this is our f of n value. And what's the complexity we got that? So this is equal to order of n log n when, sorry, n is a power of 2. So this is our condition. This is our g of n. So according to theorem. So this is f of n and this is g of n. And this condition that is to be removed. So if you want to remove that, first what are the things as per the theorem, what we have to prove that both f and g, okay, both f and g should be eventually non-decreasing. Okay, that we have to confirm. Okay, both f and g should be eventually non-decreasing. Then we have to prove that g is too smooth. Why too smooth? Because it's a power of 2. There the theorem power of p we have given. That's why p smooth we consider, but here it's a power of 2. And hence we have to prove that g is too smooth. Okay, now if you take g, first of all, let us take g. G is eventually non-decreasing. Why? N is n, we know that as far as n increases, the value increases. Log is also increasing function. So both n and log n are increasing function. N into log n, that is also an increasing function. So automatically you can say that g is eventually non-decreasing. It never comes down. Never comes down. So when the value of n increases, automatically the function value also increases. So our task is to claim that this f is eventually non-decreasing. So f is given like this, right? F is given like this. So to prove f is eventually non-decreasing, anyway, we can take a mathematical induction proof. Already we have studied that, right? The first claim is f is eventually non-decreasing. So in the mathematical induction, there are 3 steps. One is basis, then hypothesis, then the proof, right? So basis is taken for smaller value. What we know is f of 1. If you start with f of 1, it's a natural number. N belongs to n, right? So we can start from a natural number. So yes, minimum value f of 1 we can take that. So anyway, we know that for merge sort f of 1 is equal to 1. Already we have seen that. The 1 that can be written as this 1 is always less than or equal to 2 into 1 plus 2. 2 into 1 is 2 plus 2. So that means 4. So 1 is less than or equal to 4, we know, right? So this inequality equal to good. But what is this value? This value is equal to f of 2. So our function is f of n is equal to 2 times fn by 2 plus n. So if you put n equal to here, you get this, right? Put n is equal to here, you get this. So what we got then? F of 1 is less than or equal to, because less than or equal to here, right? F of 2. So for the basis condition, it holds good. Okay. So that is, this is, this is the definition of increasing function, eventually non-decreasing function. So there the definition is f of n less than or equal to f of n plus 1. So this we have to prove that. So for base condition, this is called. Now the hypothesis, anyway, we are taking a strong principle of mathematical induction, or a second principle. So for any value of m less than n, strictly less than n, okay, any value of m less than n, we assume that f of m is less than or equal to f of m plus 1. Strong principle. This is only assumption of hypothesis. So in particular, if you say something like that, in particular, we can always say that f of n by 2. Okay, this is required. That's why I'm telling that f of n by 2. So n by 2 is less than n, right? N by 2 is less than n. Therefore, by the hypothesis, that will also hold good. So that is less than or equal to f of n plus 1 divided by 2. Why? Anyway, you see, these m are integers, but there is a fraction. So actually, we assume that f is from set of natural numbers to set of non-negative real numbers. So this value should to be the integer value. So you are the integral part of that. Therefore, if you say n by 2 is an integer, and even suppose n by 2 is an integer, then n plus 1 by 2 is not be an integer. So if it is not an integer, suppose it is an integer, it goes to the next point. I mean, next natural number. If it's next natural number, automatically that hold good, no problem. So if it is not a natural number, then what happens is this value and this value will be the same. So equal to condition is also there. So we can conclude that if based on this one, this for this particular case also that holds good. Okay, now based on that, we can see the proof. Okay, in the proof, we can take f of n. F of n is equal to 2 times, that is based on the recurrence relation we got, 2 times n by 2, f of n by 2 plus n. So now based on this, what you can write? You can write this less than or equal to 2 times. Okay, this property already we have seen that. So f of n plus 1 divided by 2. And plus n, we can put plus 1 also because it's the larger one, greater than. So we can add some more value, no problem. So n plus 1. So now what happens if you combine it together? What is this value? This is equal to f of n plus 1. Now totally what you get? You got f of n that is less than or equal to f of n plus 1. So we proved. Okay, so we proved. So now we proved that both f and g are eventually non-decreasing. Now only part we have to prove that is g is too smooth. So what is our g? Our g of n is equal to n log n. Okay, that is what inside asymptotic value we have, right? Asymptotic notation we have. G of n is n log n. So if you want to prove that g is too smooth, what we have to take is we have to take g of 2n. So g of 2n is equal to 2n log 2n, right? 2n log 2n. So that is equal to 2n. So log a b is equal to log a plus log b. So log 2 plus log n. So log 2 to the base 2 is equal to 1, right? Log 2, whenever we are not taking anything, it is base 2, right? So this is log 2 to the base 2, so that is equal to 1. So this is equal to 2n, 1 plus log n. So if we expand, what you get is 2n plus 2n log n. Now you see, this is one function, this one function, we have to take the maximum. So maximum is n log n. So if you put order, this constant is not going to come. So constant won't come, right? So remaining is n log n. So that is equal to order of n log n. So if it is equal to order of log n, so we got that g of n is equal to g of n is too smooth. Okay. So as all the properties are satisfied, now we can remove the condition. So we can say that f of n is equal to order of n log n. Now it's hold good for all values of n. So this is what we do that. Theoretical analysis, we do this way. So you see sometimes the conditions are required, but the conditions can be removed when these properties are being satisfied. So that's why whenever we are saying the merge sort, okay, automatically we say n log n complexity without condition. So without condition is not just removed it. It's not just removed it. It is satisfying certain properties based on the theorem. Okay, so whenever these conditions are being satisfied, I mean the properties are being satisfied, you can remove the condition from the conditional asymptotic notation. Okay, so anyway, we cannot take more examples and explain it because time is not sufficient for that. We have to cover a lot of other things in your syllabus, but to get some basic idea, we are giving some details at one or two examples. That's all. Okay, now let us get into, I think only 5 minutes there. Okay, we can see this to some extent. Now let us go to analysis part, algorithm analysis. Okay, so far we have seen only the notation, but now in the analysis part, we have to see the best case, worst case, and average case. 3 ways we can do the analysis. One is as best what the algorithm complexity is, or in the worst what the complexity is, or on the average the complexity is. So to denote best, worst, and average, how we get that? Anyway, so far the discussion we had, given an algorithm, okay, maybe if the algorithm is very simple, something like find the maximum. So each step we consider one unit at a time, and whenever there is a for loop, depending on the number of iterations we consider, then finally we remove the constant and like that, and based on the size of the input, we represent the complexity. And another case, merge sort algorithm, based on the logic, we have given the complexity. But now we are saying that the what is the best case. So the case in the sense that you see, I mean, we can define different instances. Anyway, I can come to that. First, let me say that V of n is the best case complexity of an algorithm. How we can define this is equal to the minimum of T of I such that I belongs to Dn. When I explain, you get the idea. So this is a definition of best case complexity. Here there are several letters are being used to T, I, D, N like that. So what this I is? I is an instance. So instance in the sense that it's an input. So that's why we say, suppose you take a merge sort algorithm, you can take 15 inputs, so size of the input is equal to 15. If we take 25 inputs, size of the input is 25. So that is another instance. So these instances are some values we are giving. Okay, what values you are giving that we do not know. So therefore, but these values from where it is being derived. So earlier I mentioned that every problem what we consider is defined over a domain. So sorting set of integer value means the domain is set of integers. Sorting set of strings means the domain is set of strings. So there is a set. That set is the domain. So there is a domain. That domain we call as Dn. So this Dn, this n is just because associated with the size. That's why we are using n. But no problem with d also we can say. Okay. So the domain Dn. The domain consists of some values. From the values, if you take a collection of values, that is an instance. That instance you have given, I mean, you can give as an input to the algorithm. So if you give that as an input, it takes some time. That time is T of I. So the time, the actual time for this instance I, that is called T of I. Okay, now you know that. Now this is minimum of such T of I. Why minimum of such T of I? Maybe the instances, different instances we can give. Okay, out of all the instances, we are taking the time, the one which gives the minimum time is the best case complexity, best value, right? So now what you can say, you can define worst case W of n. W of n is just opposite. So instead of minimum, we have to take the maximum. Okay, maximum of T of I such that I belongs to Dn. So in a further explanation not required, when the value is the larger value, that's the worst value. So worst case. And the when that value is smaller value, that's the best case. Okay, it's very clear. Then what is the average case? Generally, how do you find the average of n numbers? What do you do? Suppose I ask you to find the average. What do you do?
We sum all the numbers and divide it by the total number of.
Yeah. So if there are n numbers, all the n numbers will be added, and that will be divided by n because total number of elements is n, this average. Here also, can we go with such average? Because I have different instances, right? I have different instances. For the first instance, I know what the time complexity is. Second instance, I know what's the time complexity. Like that, all the instances, and if we take the average like that, will it work?
Sir, there may be infinite instances. So
Infinite instances. So if you divide by the number of instances, something divided by infinite will come, right? So you cannot define that. But mean that therefore that kind of average calculation is not possible. It is uncertain, right? It is uncertain. And hence here we have to give the, for example, if you say A of n is average complexity, so that will be stated as sigma I belongs to Dn, P of I, T of I, P of I, T of I. So already we know what is I, what is Dn, that is correct. This T of I also we know what it is from the previous two things. And one more factor we have added is P of I. So this P of I is called average probability. So when something is not deterministic, we have to go for the probable value. You have to go for the probable value. So here we take the average probability. Okay, I got to take one example and illustrate, but time is already gone. So maybe we can see that in the next class.